As objects shrink to the nanoscale, the balance between their surface area and volume changes dramatically, and this shift transforms how they behave. At the macro scale, the volume of a material largely determines its properties. A steel beam's strength, a sponge's weight, a block's inertia. But shrink that object down to a few nanometers, and suddenly the surface dominates the game. This imbalance is at the heart of why chemical reactions and surface phenomena become far more important than mechanical properties at the nanoscale. Let us consider a simple example. Imagine a cube of material that is 1 centimeter on each side. It has a volume of 1 cm3 and a surface area of 6 cm2. Now divided into a billion smaller cubes, each 10 nanometers on a side. Each tiny cube still has a volume, but now the total surface area has increased immensely. At this scale, the surface-to-volume ratio becomes so high that nearly all atoms are at or near the surface, rather than buried inside. This shifts the balance of forces, energy, and interactions. Why does this matter? Because chemical reactions mostly occur at surfaces where atoms are less tightly bonded, more reactive, and more accessible. At the nanoscale, with a much larger percentage of atoms exposed, materials exhibit dramatically different reactivity. For example, gold is famously inert in bulk form. It does not tarnish or corrode, but gold nanoparticles can be powerful catalysts, enabling reactions such as carbon monoxide oxidation or hydrogen generation. What changed? Simply the surface-to-volume ratio. Mechanical properties also behave differently, but they do not dominate. In larger systems, strength depends on things like internal structure, grain boundaries, and stress distribution across the bulk, but at the nanoscale, quantum effects, atomic disorder, and thermal fluctuations start to matter more than bulk elasticity or strength. A single nanowire might behave like a spring at one temperature and like a brittle rod at another. Yet even these properties are often influenced by surface tension, surface energy, and atomic coordination at the boundaries. Again, surface phenomena. Now, you might ask, does this mean nanomaterials are always more reactive? Not always, but often. Nanoparticles, nanotubes, and nanosheets can be engineered to have specific surface structures that attract or repel certain molecules. This has huge implications for catalysis, drug delivery, energy storage, and environmental cleanup. Their tiny size makes them chemically lively, but also means they may be physically fragile or hard to manipulate using traditional tools. So the surface air-to-volume discrepancy is not a minor detail. It is the governing principle of nanoscience. It explains why the same material can be unreactive in bulk, but catalytic as a nanoparticle, or why nanoscale devices need new models for strength, heat flow, and conductivity. It is the reason why chemistry becomes dominant and mechanics secondary once you enter the nano realm. Would you like a table of examples where bulk vs nanoscale behavior differs? Like gold, titanium dioxide, carbon, and silica, showing the role of surface area. As objects shrink to the nanoscale, their surface area decreases more slowly than their volume, leading to a drastic increase in the surface-to-volume ratio. For a sphere, surface area scales as R2 and volume as R3, meaning that smaller spheres have proportionally much more surface than internal mass. At a few nanometers in diameter, more than 50% of atoms can be on the surface. This shift drastically changes the material's dominant behaviors, from bulk-like to surface-governed. Surface atoms are chemically more active due to unsatisfied bonds, lower coordination numbers, and greater exposure to the environment. These factors make nanoscale materials highly reactive and chemically sensitive. Gold nanoparticles catalyze CO oxidation, while bulk gold is inert under the same conditions. Like having a crowd where most people stand on the perimeter, what happens on the edges suddenly matters more than the center. At the nanoscale, quantum confinement alters the electronic structure of materials, affecting band gaps, density of states, and orbital availability. These changes impact how molecules adsorb, dissociate, and react at surfaces. Electrons become more localized, increasing polarizability and facilitating charge transfer during reactions. Quantum effects can make previously inactive surfaces chemically active, modifying catalytic efficiency and select. These electronic shifts often enhance redox properties and energy level alignment with reactants. Such fine-tuning of electronic states is impossible in bulk materials. Quantum dots show size-dependent fluorescence due to quantized energy levels, and similar effects enhance catalytic specificity. Like tuning a radio to the perfect frequency, small size lets the system resonate precisely with the signal or reactant. Mechanical properties such as stiffness and yield strength arise from bulk atomic arrangements and long-range order. However, at nanoscale, the contribution of surface energy becomes dominant in determining mechanical behavior. Surfaces can induce strain, curvature, and instability not observed in bulk forms. This leads to size-dependent melting points, unusual elastic moduli, and even negative thermal expansion. Since chemical interactions are governed by surface energy, they override mechanical rigidity in importance. Mechanical properties can still matter, but they are modulated by surface effects, not vice versa. Nanowires of zinc oxide bend and flex under minimal force due to surface-induced softness, despite being brittle in bulk. A thin soap film behaves very differently from a glass window. Same material atoms, but surface tension rules one and rigidity the other. In bulk materials, Gibbs free energy changes are largely volumetric, but at the nanoscale, surface enthalpy and entropy dominate thermodynamics. This leads to enhanced solubility, phase transformation rates, and chemical reactivity. Reaction equilibrium can shift because the surface energy contributes significantly to total energy, especially in multi-phase systems. High surface curvature leads to higher chemical potential, accelerating reactions that are slow in bulk. Therefore, nano-objects more readily undergo oxidation, dissolution, and catalytic interactions. These effects are central in nanomedicine, corrosion, and environmental remediation. Silver nanoparticles release ions faster and show stronger antimicrobial effects than larger particles. Like sugar dissolving faster when powdered, tiny size increases contact area and drives the process. Nanoscale materials often exhibit high densities of surface defects such as steps, kinks, vacancies, and grain boundaries. These defects serve as reactive hotspots, lowering the energy barrier for chemical reactions. Even a nominally inert material may become highly active if its surface is riddled with low coordination sites. Such features also bind molecules more strongly, increasing residence time and facilitating bond rearrangements. In bulk, defect density is low and often buried inside, contributing little to reactivity. Nanoscale materials exploit this defect-rich interface to drive catalysis and sensing. Platinum nanoparticles with rough surfaces outperform smooth single crystals in hydrogen evolution reactions. Like a jagged coastline providing more harbors for ships, rougher edges offer more entry points for interaction. At the nanoscale, atoms on the surface have greater mobility due to lower coordination and weaker binding forces. These atoms are more susceptible to thermal excitation, leading to dynamic rearrangements, surface diffusion, and local restructuring. Such mobility allows continuous formation of reactive sites and adaptation to the environment, critical in catalytic cycling. In contrast, bulk atoms are locked into rigid lattice structures and cannot reorganize easily. This dynamic behavior enhances surface reactivity and self-healing in nanoparticles. Surface mobility also plays a role in sintering, Ostwald ripening, and catalytic regeneration. Iron oxide nanoparticles restructure during catalysis to maintain activity under harsh conditions, like a flexible team that constantly adapts roles. Nanosurfaces are agile and reactive, unlike rigid hierarchies. Chemical reactions require diffusion of reactants to active sites and products away from them. In nanoparticles, short diffusion paths ensure that almost every atom is either a surface or a near-surface site. This drastically enhances reaction kinetics, especially for gas-solid or liquid-solid interfaces. Because reactants can access most atoms without penetrating deep into the structure, reactions proceed faster and more uniformly. And this benefit is critical in energy devices, catalysis, and drug delivery. High surface accessibility turns the entire particle into a functional unit. Lithium iron phosphate nanoparticles enable fast charge/discharge cycles in batteries due to short ion diffusion paths. Like a small island where everyone lives near the beach, no one is far from the action. In bulk solids, mechanical integrity arises from long-range crystal coherence and collective dislocation motion. At the nanoscale, such coherence is lost and dislocations cannot form or propagate easily. Mechanical deformation shifts from collective to localized behavior, often governed by surface rearrangements and atomic slips. Therefore, materials may become harder or softer depending on boundary conditions. Yet these shifts are less impactful than chemical reactivity changes since few nanosystems are used structurally at their scale. Chemical behavior dominates because reactions can occur regardless of long-range order. Gold becomes stronger in nanowire form but is chemically much more active. Like removing bricks from a wall, its ability to carry load changes, but if it's soaked in acid, it dissolves regardless. The dominance of surface reactivity at nanoscale is exploited across multiple industries. Catalysis benefits from higher turnover rates and selectivity via engineered nanoparticle surfaces. In medicine, nanoparticle coatings can react with specific biomolecules for targeted therapy or imaging. In energy systems, surface-driven reactions underpin hydrogen storage, fuel cells, and photocatalysis. The mechanical aspects of these particles are often secondary or intentionally suppressed. Ultimately, surface area governs usefulness more than strength at these dimensions. TiO2 nanoparticles used in photocatalysis convert pollutants using surface reactions activated by UV light. Nanoscale materials are like matches. They burn quickly and effectively, but are not meant to hold up a building.